All right, so what we're going to do is we are going to work on review for the atomic structure. So I'm going to go through these questions on the review sheet. And so the first thing, it says know the location, purpose, and charge and size of the protons, neutrons, electrons. Well, that's in the PowerPoint. So you do need to know that, and you need to know that protons are +1. They're in the nucleus. They're 1 AMU, and the purpose is identity. Neutrons are in the nucleus. They're neutral. They are mass of 1 AMU. Purpose is stability. And the electrons are about 1/2000th an AMU, and they are outside the nucleus. They have a negative charge, and their purpose is going to be reactivity. And then we have this little chart, which you already had a quiz on. Make sure you know your terminology: mass number, atomic number, isotope. Be able to recognize what each of those things are, be able to calculate those things, as well as identify isotopes, identify neutral atoms, etc. All right, so if we want to go from the hyphen notation to the nuclear symbol, remember the mass number, which is after the hyphen, goes up top. I look at the periodic table to get the atomic number, and that is 32 for germanium. And then I put a GE. It does have a charge of +2, so I put a 2 up top. And remember, it goes mass number, atomic number, charge. From this, I can get the protons, 32. Neutrons is mass number minus protons, that's 42. Electrons, if it's a +2 charge, it means it lost 2 electrons. So if it started with 32 in a neutral atom, it means it's ending with 30 electrons. To work the other way, I have 42 protons, 40 electrons, which means it has a charge of +2 because it has 2 more positives than negatives. I look on my periodic table and I find out what element it is. 42 is molybdenum. And then the mass number is 42 plus 55, that's 97. And then it's a charge of +2. Now, if the mass number doesn't match the rounded number on the periodic table, that's okay, because it is an isotope. And then you can write MO, or the full word, 2 plus hyphen 97. When we have our nuclear symbol, it's going to be nitrogen. It's got a 3 minus. Hyphen 15, number after the hyphen, is the mass number. Protons is 7. Neutrons is 8. Electrons, if it's a -3, it means it has 3 additional electrons, so it's 10, and the charge is -3. Okay. Question 3, we have element Z has 2 naturally occurring isotopes. The weighted average is 79.35. What is the percent abundance? So you need to set up your little system of equations. So overall, it's 79.35. We're going to say the isotope with a mass number of 78 is going to be X. And then we're going to add that to the isotope of mass number 80, and we are going to do 1 minus X. Now, if you do 100 minus X, you can do that as a percentage, but then remember you have to multiply that number times 100. We are then going to use our algebra to solve for this. Look at the answer key for how to work that out with the algebra. And I get X equals 0.325, which means that is 32.5% for the isotope 78, which means the isotope 80 is going to be 67.5% because the 2 percentages need to add up to 100. 4, we have 2 isotopes. We have a percentage and we have a mass. So it's going to be percent times mass, plus percent times mass, plus percent times mass until you run out of numbers. So we have 19.9% is 1 isotope times the mass that goes with it is 10.013. And then we have 80.1% times the mass that goes with it, which is 11.009. We only have 2 isotopes, so we do that twice. We're done, and we get 10.81. It makes sense that it's closer to the 11 because 80% of it is the isotope with the mass number of 11. Now, this you can very easily check because you can look at the periodic table. But I'm going to most likely give you problems where you cannot look at the periodic table, so make sure you know how to do the math. All right, fill out the following chart. So we have different half-lives for different substances. So now if we have radon, so radon's right here, and we have 1,500 grams, how much will remain after 44 days? Well, our initial amount is 1,500. Our final amount is what we're solving for. It's going to be 1/2 raised to the number of half-lives. Well, I have 44 days. Half-life is 4 days, so it's 11 half-lives. So it's going to be 1/2 raised to the 11. So to hit that into your calculator, it's 1,500 divided by 1/2 caret 11. And when we solve for this, we get a final amount of 0.7324 grams. All right, after 10,000 years, 0.591 grams of C14 are present. What was the mass that we had 10,000 years ago? Okay, we're going to use the same formula, but I'm looking for the original amount now. So X is going to be my final amount, 0.591, times 1/2. And now I have to figure out how many half-lives have gone by. Well, I have 10,000 years. The half-life of carbon-14 is 5730 years. And I get 1.745 half-lives. So the 1/2 is raised to 1.745. I do the math, and I get 1.98 grams. So I started with 1.98 grams, and now have 0.591 remaining. All right, a 25-gram sample of iodine decays to 0.872 grams. How many half-lives have passed? All right, so this is one we're going to have to use the log button. So I started with my initial amount was 25 grams. I'm going to multiply that times 1/2 raised to some power, and that equaled 0.872 grams. So what I have to do is I'm going to take 25 divided to both sides. So I get 1/2 raised to the n equals 0.03488. And then I hit that magic button on my calculator, the log button, and I take the log of both sides. So what I end up with is the log of 0.03488 divided by the log of 1/2, which is 0.5, is there. And that will give me the number of half-lives that have gone by. And so N is going to be 4.84 half-lives. Okay, so you have to use the log button to solve for that one. In number 8, we have to do the same thing. So 8, what is the half-life of a radioactive isotope? If 500 grams decays to 62.5 grams in 24.3 hours. So we're going to have to solve for our N and then get our half-life from that. So our original amount is 500 grams. We have to multiply that times 1/2 raised to the n, and we end up with 62.5 grams. Divide both sides by 62.5. I'm sorry, both sides by 500, and I get 0.125 equals 1/2 to the n. Then I take the log of both sides. It's going to end up being the log of 0.125 divided by the log of 0.5, and I get n equals 3. So 3 half-lives have gone by. Well, that 3 half-lives is split between 24.3 hours. So I take 24.3 divided by 3, 8.1 hours. And I got that because the time divided by the number of half-lives equals the half-life. Okay? Or we could do time divided by the half-life equals the number of half-lives. It's the same formula, I just rearranged it. We have been using this to get the n value, now we just rearrange it to get the half-life. All right, so make sure you also know alpha, beta, gamma. Alpha is a helium particle, symbol 4/2, or it's the fish, 4/2. It's the least penetrating. Beta is going to be 0/-1. It's an electron, or a bee with a long tail. That is middle penetrating. And gamma is the dead fish, 0/0. It's the most penetrating. It is just energy. Okay, filling out nuclear equations. You're basically just doing algebra. Numbers on the top, on both sides have to be equal. So I'm just going to do a couple of these, and then you can just look at the answer key. So on this side, I have 59 plus 1 is 60. 60 plus 1 equals 60. Well, that's got to be a 0 on the top. 27 plus 0 is 27. 27 on the bottom, so it's got to be a 0. The particle that's 0, 0 is a gamma. For the next one, 40 plus 2 is 42 on the top. So 41 plus 1 gives me 42. 19 plus 1 is 20. 18, oh, I'm sorry, it's 18 plus 1 is 19. And then 18 over here, 18 plus what? It's got to be 1. So it's going to be plus hydrogen. So we're doing hydrogen 2, combining and then giving off hydrogen 1. Over here we have 18 at the top, which means this has to be 17, because 17 plus 1. I have 9 at the bottom. Over here it has to be 8. You look at your periodic table, oxygen is 8. 18 at the top, 18 at the top, so it has to be a 0. 9 at the bottom, 8 at the bottom, it has to be 1. This is actually a positron. I am not going to ask you about positrons, but it is here, so we're just continuing. I'm just going to do one more. 9 plus 4 is 13. 4 plus 2 is 6. 12 plus what is 13? 1. 6 plus what is 6? 0. 1/0 is a neutron. Okay? You do exactly the same thing for the rest of the way down. You're going to look at your answer key. And then the last part is just writing a nuclear decay equation. So the first thing we're going to do is we're going to write the nuclear symbol for what's given here. So samarium 153. 153 is the mass number. 62 we get from the periodic table. The symbol is SM. And it's going to decay. So we're going to start with one thing. Anytime we have a decay, we have one reactant split it into 2 or more products. So what's being given off? An alpha particle. Alpha is 4/2 helium. Well, then I need to do what I did above. 4 plus what is 153? 149. 2 plus what is 62? 60. So that is neodymium. And then the last one, beta decay of ammonium, 166. I convert that to a nuclear symbol. Holmium has an atomic number of 67, and the symbol is HO. Decay means it's one thing breaking into 2 or more. It's got to be a beta decay. Beta is 0/-1 electron, or beta. 166 plus 0 is 166. This is 68, because 68 minus 1 is 67. And then you look on your periodic table, it's erbium. Okay, make sure you look over the review sheet, look over any sample problems we have done in class, and good luck on your test.